So maybe I get confused myself. Of course, this is just a convention. Let me see what I did. I did this quite a while ago. Let me see. So AY would be rotations about the y-axis. So that will be, it's complicated here. 2, 4, 3. And then AX would be 4, 1, 3, 2. So is that equal to C2 or not? C. Yes, isn't that the same? I mean, C2 is counterclockwise by pi, right?
Yeah.
Yeah. So then I got the right ordering. So if we take AX and let's say, oh, what did I? AY.
But then it doesn't matter because AX and AY.
Because I see.
They commute, exactly.
That's true. So if I take D1, okay. Of course, this doesn't matter. It's just a matter of convention. It depends on how you define this. You can define it any way you like. So maybe we should not spend so much time on this because it's okay as you have it here.
Yeah. Okay, then I will continue.
So let's see. So in your table, how do you define it now? Which X first?
I define it as we have the row element multiplying the column element, but the column element acts first because we are multiplying to the right, so it becomes AX, AY, and then our object to the right of it. So AY happens first.
Yeah, so that's what I mean. That's exactly what I mean. So you have
the column happens first, but we write it AX times AY.
Yes. So AY actually X first, and then followed by AX.
Exactly.
Right? Yeah.
Exactly.
So that's what I have here. Yeah. I think that's what usually what we mean. Okay, so let's continue then.
Yes. So we obviously get the trivial class, just the unit element.
Yes.
And then we start by putting in AX in the middle, and then just put all the other elements on each side. Yeah. All elements except for C1 and C3 are their own inverse. So we can just, from the table, we get the first values here and the inverses vanish.
Yeah.
And then we see that AX is conjugate to itself. AX is also conjugate to AY. And then C3's inverse is C1. And we also get AY here. So then we get a class of AX and AY.
Yes.
And then we go on to put D1 in the middle instead. And we see that we get D1 and D2 are conjugate from each other. So this is another class. And then we put C2 in the middle. And we see that C2 is only conjugate to itself. So it forms a class on its own.
Yes.
And then C1 and C3 form a class together.
That's correct, yes. So do you see any geometrical meanings in this? I mean,
well, yeah, our class here is both rotations or flips along the X and Y axes. Well, these are both flips along the orthogonal diagonal axes. Yeah. And these are both rotations that undo each other. And this is just a rotation around the z-axis instead. And it's the only rotation around the z-axis, so it's alone.
So it's a bit interesting that the C2 form a separate class than C1 and C3. One would intuitively think that they belong together, but they don't yet. Okay, good.
And then we have our subgroups, which we can easily see by looking at the multiplication table on which ones we can multiply together to stay within a subgroup. So, for example,
Yeah.
The identity element and each element on their own form a subgroup. But then we also get a few more subgroups, like for example, the unit element and C1, 2, and 3, which we can see from the multiplication table, because in this cube here, we either get the unit element or one of the other elements in the subgroup. So we stay within the group. And then in the same way, we see that AX, AY, and C2 forms another subgroup, and the diagonal elements in C2 form another subgroup. And if we include everything except for AY and C2, we get another subgroup. And the same thing if we switch AX with AY.
Can I interrupt you there, actually? Because I think some of these don't agree with my solution. For instance, the group 2S2 that you call there with E and AX. AX has no inverse in this group, right? So it wouldn't be a group.
No, AX is its own inverse. So if you look at this part here, E times AX is just AX.
You didn't. Oh yeah, you're right. But you didn't have a group with E and C1.
No, exactly, because they're not their own inverse.
Yeah.
So only these that are their own inverse stay.
Then I agree with you. Yeah. Okay.
EC2.
And then check for which are invariant. We just we see if the left and right cosets are the same. So we see obviously the trivial subgroup is invariant for any A. And if we look at S6, for example.
Let me see. Can I interrupt?
Yes.
You have, let's see, how many elements do we have here? We have 8 elements, right? 2, 3, 4. Yes. We have 8 elements, and then you have S10 and S11. So that has 6 elements, right?
Oh, you're right.
So they cannot be subgroups, because you know there's.
Right. I probably made a mistake when looking at the table. Oh yeah, I think one of these combinations can get us to
different element outside.
Because AX and D1 and D2 gives us C3 and C1. AX and C1 and C3 gives us D2 and D1.
Yeah.
So I'm not sure how we can get outside the group, because AY isn't in the group and C2 isn't either in the group.
If you take D1 times D2, you get C2, which is not in the group.
Yeah.
Or C1 or C3.
Yeah, that's the ones I missed.
Yeah.
Thank you.
Shouldn't you also have this that it is divisible? Or
Yeah, that's it. So
exactly. Yeah, I had forgotten about that. So. Yeah. So then we can ignore these two.
Yes. Okay, so that.
So there's 9 subgroups.
Yes.
Is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, if you include the unit element. Yeah.
And then for the invariant subgroups, we see that, for example, since C2 takes AX to AY, D1 to D2, C1 to C3, and etc., that S6 becomes an invariant subgroup, because if we multiply by D1, for example, from the left, we get D1, D2, and if we multiply by the right, we get D1, D2 as well. So S6 becomes invariant. S7 becomes as well, because if you multiply C3 from different directions, they give you opposite results. And then for the same reason, S8 and S9 become also invariant.
Yeah, that's true. But there is also a simple way of looking at this. So if the subgroup is invariant, what's the characteristic of this group?
So it's made entirely of classes,
Exactly.
but I don't know if that's an if and only if.
So all those invariant subgroups should just be classes.
Yeah,
consist of
yeah,
classes.
you're right. This is the first class and one of the classes, and this
Is
is
that
three
an if and
classes.
only if? Sorry, is that an if and only if condition? So I see that it is true for each invariant subgroup that it is made
Yeah.
entirely of classes.
Yeah.
But is it true that all groups which are made entirely of classes are invariant subgroups?
Well, it should be, right? I mean, oh, well, no. I mean, let me see. Good question. I guess so, because if you have classes, then by definition, you have this invariance with respect to similarity transformation.
Sure. Yeah. Okay. Yeah.
So then, if the subgroup consists of classes, then I suppose it has to be invariant.
Yeah.
Because it fulfills the condition of being invariant under the similarity transformation.
Yeah. Sure.
Yeah.
So in that case, you just look at which, because you have the groups already. And then you look at-
Yes. So you know
And
the
we
classes.
already have the
right?
classes.
We have the classes. Yes. So we just Mhm. So I think that's correct. S1, S6, 7, 8, and 9. Yeah.
That agrees with
Very
my
good. Mhm.
And then we have the cosets. So
Yes.
from S1, we can obviously form a coset with every element, since it's just a unit element. So that was not very interesting. But for S6, if we multiply it by AX or AY, we get a coset of just AX and AY. And the same thing if we for the diagonal elements, and similarly for the C1 and C3, since the unit element becomes one of them and C2 flips the other one.
Okay.
And then for S7, we only have one coset because AX gives us, the unit element gives us AX, C2 gives us AY, and then C1 and C3 gives us the diagonal element, which becomes the same as the other cosets. And then similarly for
Okay. Let's see.
the other two.
So let's go back to the S6. What do you have for the S6? Or the S1, let's say. Let's do this one by one. So your S1 is which one now?
S1 is the trivial one, so that just becomes a coset.
I see. So that's trivial. So let's take
S6 was E and C2.
Okay, so let's take S6, let's say.
So
And
AX
you have-
times E gives us AX, and AX times C2 gives us AY, and similar for these two.
Okay, so then you have 4 elements, four cosets.
Exactly.
Yeah.
We have the trivial one and then the others.
Mhm.
Well, for these we only get 2, the unchanged one, and all these become the same one.
Mhm.
And same thing for 8 and 9.
Okay.
And then now we're supposed to find a factor group. Obviously, the factor group dividing the trivial group is isomorphic, since we're just since the group of cosets is just a group, since each coset only includes a single element.
Yes.
And then for with S6, we have S6 as our unit element, and then AX, D1, C1. AX times itself is just the unit element, so we get back S6. D1 times itself also gives us just the unit element, so we get back S6.
Right.
And C1 times C1 gives us C3, but since but on S6 C1, I think
No, I
I might
think
have written this wrong.
you're correct. I think because C1 times C1 is C2.
Oh yes, you're right. Sorry, exactly. C1 times C1 is C2, which leaves the group unchanged.
If you
And then we
get
get the
the unit element.
and exactly. And then on the diagonal ones, we get AX and D1 gives us C1. Same thing here with AX and C1, and then C1 and D1 gives us then AX.
Yeah.
So then we get our factor group.
Yes.
Well,
So,
the others become
can
pretty
I
simple.
just comment?
Mhm.
So actually, if you look at the multiplication table there of the factor group, you see that they are diagonal. It's diagonal, right?
Yes,
So that suggests what?
that it's abelian.
It's abelian, yeah. It's abelian. And why is it abelian?
I'm guessing since we've divided out the, if we look at S6, I guess since C2 commutes with all of them, I think
Right.
that makes it abelian.
Yeah. So actually, if you look at all the elements like AX S6 and then D1 S6 and C1 S6, they are all made of classes. So
Like
the first
exercise 3, right? Exercise 3.
Yeah.
You prove that, right?
So if you look, let's say the first one, what was it? AX times S6. What do you have?
Yes, it's AX AY.
Yeah, which is from a class, right?
Yes,
And D1 S6, what do you have?
D1 D2, which is
Which is
also
also
a
a
class,
class. Yeah.
and C1 C2 is also a class.
Yeah. So that's why they commute, right? Because you have classes. Well, there is actually the next problem there, but yeah, if you have two classes, you multiply it and they commute. Yeah. So
And then
classes
we have the others become just trivial. Since
Yeah.
we only had two.
It's easy. Yes. Okay.
Yes, then I'll let someone from the other groups present the other questions.
So are there any questions for this problem 1? So everything is clear. Are there any things which are not obvious or not clear? Okay. If then we can continue, I guess, if everything is okay. So let's see what the time is. Okay, still have we have plenty of time. So if there are no questions, then maybe we can continue with the next question. So the second group is supposed to give a presentation for the solution. So who is going to volunteer?
I could start presenting.
Yeah.
Let
I think.
me just share my screen.
Yeah. So I think the next set of questions are quite straightforward, except maybe the last one. You have to think a little bit more.
Do you see my screen now?
Yeah.
So I will
Very
just more or less read. So yes. So if the group is finite, then the class will be finite as well of that group. So if we have a class with some elements and we know that we have a finite number of elements, and then for each element there will be an existing integer where that element to the power of that integer will be the unit element, because otherwise the class would not be finite. And we can choose the smallest of these integers to be ni, and just denoted by n.
Okay.
And then we express ai to the power of n in terms of another element in the group, because we know that there are elements G that for which this relation holds.
Yeah.
And for every aj in this group.
Yes.
And since we already know that ai to the power of n is equal to the unit element, sorry, we can just do the work out the multiplication, and then all the g inverse will cancel, which means that we end up with this expression. And from this it follows that also aj to the power of n is equal to the unit element.
Yes.
And since this means that since we said that n was the smallest integer for any element in the group that this relation holds, it must
Yes.
be true that the order is the same for all elements.
Yes. I think that's correct. Yes. So is it clear with everybody? So it's just basically verifying that all elements in the class have the same order as it's been done here. So just take the power. So this is basically because the similarity transformation doesn't do anything to the elements. It gets back to the same class.
Yes.
So it just brings from one element to another. Yes.
Yeah. Does
So
anyone
it's-
else
I think
want
it's
to
quite straightforward. Okay, so if it's clear, I guess. So we can continue maybe with this third problem.
Is there anyone else in group 2 that wants to present the next problem? Otherwise, I can talk about it. It's quite short.
Okay.
Yes, so we want to prove that classes commute in the sense that we get the same elements if we multiply them from left to right with each other. And we can see this by the fact that for classes of group G, we have that for any element in group G, and this holds G Ci, G inverse is equal to G Ci. And
Yes.
we can, I think we also showed it in the lecture notes, but it's quite clear from the definition of the class that this is true.
Yeah.
And if we take this expression and just multiply it with G to the right, we see that this holds.
Yes.
But since all elements in this class is in G, we also have that the relation holds for all elements in the class, which means that we have proven what we wanted to prove, because we see that Ci commutes with all elements in Cj, which means that the class commute.
Yeah. So you just sum over the elements in the given class. Well, actually, it doesn't even have to be a class. So Cj, I think, can be anything basically.
Yeah, we already showed it here that as long as G is an element in
In
G,
G,
then they will commute with the class.
Okay, so I guess that's also quite clear. Any questions about this problem? Okay, if yeah, I think it is quite clear. Yes, maybe we can continue with a fourth problem.
Yes.
So
Uh,
anybody in the second group wants to volunteer? Yeah, well, present solution. Oh, it seems we have plenty of time now.
If
I
no one
think
wants,
have the solutions in a presentable way. Like I just have it written on my notebook. I didn't really actually think about that, which I guess was a mistake. Should have written it out in a nicer way.
Mhm.
But
You want to share a screen or something?
actually, it's in my notebook, so I'm just thinking if there would be a good way to share that. But
You have to um, you have to let me say the previous presenter should take off. Yeah, sorry. So you can share a screen now, I guess.
oh no, I think I said
You just want to.
can I actually I could write it out. I could do that. Yeah, sure, I could do that. Could write on my screen. If you given it, my laptop is getting a bit slow. Sorry about that.
No problem. Just take your time. We have plenty of time.
So can I just then intervene with a question on the last exercise that we just talked about?
Okay.
So we saw that CI commuted with some element G in the group, but it might change which element in CI, right? Isn't that true? We have what he showed before on the slides. He said that a similarity transformation of CI, you get CI back, but obviously you can change which element in the class, right?
Yeah.
And so then he multiplies them right by G from the right. So
yes.
Then what he showed is that G times CI is CI times G.
Yes.
But it might change which element in this class CI, right?
It might change the elements in the class CI.
Like, yeah.
Let's see if I understand what you mean. I mean, we have a set of elements in CI.
Yeah.
And then we do this similarity transformation. So then these elements in the class CI will go back to themselves.
Right, but when you write CI, you mean one particular element in CI, like any one, but it's a particular element, right?
No. When we write CI, we mean a bunch of elements.
So it's like a list of them or a set of them.
Yes.
Okay.
Yeah. So not a single element. Yes.
Right. But okay. But suppose you have an element of CI. And you multiply from left by G or from the right by G, they're not necessarily the same.
No.
Right. But if you have two different elements of CI, then for each element of CI, you can find another element of CI such that G times CI and G times the other one. Does that make sense?
Let me see. I understand that.
I'm thinking like this.
Okay.
And then G, X, Y, G, but X is not necessarily equal to Y.
Yeah, that's correct.
Yeah, this should work, right?
That's fine. Yeah,
Okay, thank you.
that's correct. So if you do rotation, so that by rotation I mean similarity transformations, then the element is brought to another element. In general, but it's within the same class.
Yeah.
So if you think about this in terms of operators in quantum mechanics, it just means that you rotate the basis. Yes, you express one operator in terms of different bases. Basically, you rotate the Hilbert space, and of course, they are then kind of equivalent. So similarity transformation simply means that you have two equivalent operators related to each other. So that's probably why it's called similarity transformation, because the two operators become, they're similar or equivalent.
Right, thank you.
Good. Yeah, it's an important question because it's a very basic properties of operators that they are invariant under also if they belong to the same class, then they are invariant under similarity transformations. Okay, shall we continue with the next problem, or you want to take a little break?
I think the next problem is not that
not too
long.
long.
So
Yeah, I think it is short. Yes,
yeah.
we can continue.
So essentially, this problem entails showing homomorphism between groups of order, cyclic groups of order 2 and 3.
4
2 and 4. I'm sorry. Yes. As a slip of tongue. I don't have it in a presentable way written, so I'll just write it live.
Yeah.
So if we think about a cyclic group of order 2, it would have a form something like this.
Yes.
Or we could just skip the A, actually A1, I mean.
Yeah, just call it
so
A.
We could just call it E and A just for simplicity. And then if we think about a cyclic group of order 4, it would have a form, say E, B, B2, that is B times B. And then B3, that's 3 times. So we have B times B times B.
Okay.
And essentially, B to the power 4 would be E, and A to the power of 2 would be E. That's the
definition.
That's the definition, exactly. So we could have, to show the homomorphism, I'll just, what I did is I essentially showed it by brute force, but it doesn't take that long. So if we take the relation, if you consider the first group of order 2, and then we take E times E, that gives us E. Secondly, we could have A times A, which gives us E again. And third, we could have E times A, or A times E, since it's an identity element, it would be the same. That would give us A. And now we say E is associated to E and B2.
Yeah.
From here, maybe I could draw some arrows to show that.
Yeah.
And then A is associated to B and B to the power 3. So to show this, I could write it out. So since we say B and B3 are analogous there, to E. So the first type, we have E times E. So we could have B times B in the same fashion, which would, sorry, wait, it was E times E. My bad.
So maybe you should write the homomorphism. So for example, E is associated.
Yeah. So E times E, that would give us E again. And then the other element that E is associated to is B2 and not B. That was my bad. So B to the power 2 with itself would give us B to the power 4, which is again E, which here is associated to E in the first group. And similarly, we could take the type 2 operation, which is the elements associated to A. So
You need
elements
to check-
associated.
Sorry, Sam, you need to check E times B2 as well, right? It
Uh,
works, it still works, but
So
oh, yeah,
maybe
that's true. I agree. That I agree.
so can we write the homomorphisms like E is associated with E and B?
Yeah, that's a good
It's
idea.
easier to
E and
follow.
B2. Yeah,
Yes.
definitely. That's very helpful, actually.
Yes.
And then I could write
B and
out.
3.
Yep.
Right. That's fine.
Yep.
Then we can see clearly what's going on.
And then we could also go with E and B2, which gives us B2. But B2 is also associated to E. So we still say within the same association. And now we can move to a type 2 operation, which is the elements, both elements are associated to A. So here we could do B times B, which gives us B2, which is associated to E. And that's what we have here. And similarly, we could do it for B3 times B3, which should give us B2 again. That is associated to, oh, sorry, that should not be an equal to sign. Associated to E. And
but
we could also do. Sorry?
Wait a second. So what is the homomorphism here? So you write B times B is equal to B squared. That's of course correct. And that's equal to E. So what is then the homomorphism?
The homomorphism is between E and B2 and A and B and B3.
Yes.
That's the question.
Well, I mean, if you take B, so B belongs to A, right, or associated with A, right? So now you take B squared, B times B, and that is equal to E. So so what is the corresponding multiplications in the smaller group? You have a group E and A, yes. So
with corresponding multiplication to E and A. Yeah, this type.
Yeah.
So the one that you underlined. So the second type, it's essentially we take both the elements from which are associated to A. So if we talk about the type 2, then we have these two elements. So we could have either B and B. We could have B3 and B3, or we could have B and B3. So these are the three possibilities, right?
Yeah. So what I mean is you would like to check that it fits with the homomorphism. So for example, if you take B times B, that's equal to B squared, and that's equal to E, of course. So now B belongs to the A, yes? You associate B with A. So then B times B would correspond to A times A.
Yeah.
So that fits. A times A is equal to E. You see what I mean?
Yeah. So B times B would give me B2, which is associated to E. Is that the question?
No. So you have this homomorphism, yes, between E. So you have the group EA, and then you have the other group with 4 elements: EB, B squared, and B cubed.
Yeah.
So now you associate the unit element in the first group to E and B squared.
Yep.
And the unit element A, the element A with B and B cubed, right?
Yep.
So the homomorphism means that if I multiply an element into one, let's take B, for example. You take you multiply B by B. So you are in the, that would correspond to multiplying A and A.
Yeah.
So you should then end up in E, which fits. But you see the meaning of this homomorphism.
Yeah.
Okay, good.
I think it's we do say somewhere that if you want to show homomorphism for finite groups, I think it's enough to prove the closure property, right?
Yeah, but also you want to prove that any element belonging to, let's say, E. So this you have E and B squared. If you take any of them, okay, and you multiply by another element in, let's say, in A, then the result should end up in A.
Yeah.
Because that corresponds to multiplying E by A, which gives you A.
Yeah, exactly. Yeah.
So for example, if you take B squared multiplying by B cubed, well, then it should be the result should be in A.
Yeah.
Yeah. So B to the fifth, B to the fifth is equal to B, which is in A.
Can I just interject then? Is there a better way to argue this? Because I feel like it's a question of notation. Because I think the homomorphism is clear and it works, but in order to check it, do you have to check every combination? If you have 4 elements, that's fine, but if you have 100, that's not fine anymore, right?
Yeah, exactly. What I was doing is here was brute force.
Is there a more general way to do it?
More general way. I mean, we know the general theory that they should work. I mean, of course, we don't have to check this one by one in general.
But is there a better way to prove that two groups are homomorphic? Because what I was doing here is, since we have to show the closure property, I was just exhausting every possibility that we could have between those two groups to show that actually it is homomorphic. But is there a more, say, elegant way or a shorter way to present the same thing? I think that's what Conic is getting at.
I don't know if there is any general way. I mean, if you have this invariant subgroup, then you can show, yes, you can show in general that the factor group is homomorphic to the original group. But here, it could be that this group is also a factor group. Again, we can see if it is a factor group or not. We can think of this as a factor group. A and B squared. So E and B squared presumably forms an invariant subgroup. Hello?
Yeah.
Yeah. So that's one way of seeing it. But for this case, of course, it's very simple. So you can just do it by hand, so to speak.
Okay. I could finish it. It's just essentially writing this out if you want me to, but yeah. So if we take another element from E and another element from here, that's what this essentially is. That would be B, but it's same for both of those elements identity, so that's quite trivial.
Yeah.
But we could consider a slightly more exciting case where we could have B2 and B, let's say that would give us B3, which is associated to A, or B2 and B3, which gives us B5, but there's no B5. So you get back to B2, which is also
To
wait,
B.
no, we get to B. Never mind. I'm a bit sloppy. My bad. Which is also in A. But yeah, that's about it. Like we just exhausted all possibilities to show the homomorphism.
Yeah.
Yep. That was about it. Alright, sure.
So yeah, so that's just a simple example of homomorphism. As I said, one of the general thing one can say about homomorphism is that if you have this factor group, then you can you have a general homomorphism between the factor group and the set of elements in the original group. But I don't know how general this is. I think that is also true for the cases that we just considered, because these are all cyclic groups and they're abelian, and then the subgroup must be invariant also, because each group forms a class. Yeah, I've never thought about it, but I don't know how you do this in general. I mean, if you given some arbitrary group. So normally we have this invariant subgroup, and then we know we can take advantage of the homomorphism between the factor group and the original group. So it's very useful when you work out the character table. I think we did that in the last lecture or so, or maybe second last lecture. And we construct the character table of the S3 group. We make use of the factor group. So is there any question in the last problem? Everything is clear. So isomorphism, I think, is clear. It's just a one-to-one correspondence. But the case of homomorphism is a little bit more involved. So it means that if you take an element in one group and multiply by another element in another group of elements, then the result should correspond to the result of this multiplication should end up in another group that corresponds to, I don't know how to explain this, it's a bit difficult. So let's say that you have group A, element A corresponding to elements alpha 1, alpha 2, and so on. And another element B corresponds to beta 1, beta 2, and so on. And the C corresponds to gamma 1, gamma 2, and so on. So now if you, let's say that AB is equal to C, then if you take any element in the group A and multiply by another element in group B, then the result of that multiplication must end up in group C. That's what is meant by homomorphism. Yeah. Okay, so maybe we should take a break. Let's say we meet at 11:30, and we do the last one, which is maybe more. I should have enough time to do the last problem. Okay. Is it more? Okay, so maybe we can continue with the last problem. It requires a little bit more thinking maybe compared to other problems. So anybody from the second group wants to go through this problem? Any volunteer? So anybody would like to try the last problem? No?
I could maybe try.
You could try? Okay.
Yeah, partial shoot solution.
Yeah, we do it together. Okay, let's try.
Yes. Hold on.
Can you share?
Yeah, sorry.
Yeah.
Okay. So our first task is to show that this is a group.
Yes.
And our elements range from 1 to p minus 1.
Yes.
So our biggest concern is that we don't want the element 0 to be in the group.
Correct.
But it won't be in the group since p is a prime number, so it cannot be factorized, which means that if we multiply two elements in the group, they will never be 0. So therefore, so when we take something modulo p, it will be between 0 and p minus 1. And we cannot have that the multiplication is 0. So therefore, if we have two elements in the group, the product is also in the group. And
yes, but can you write it down in the more kind of algebraic manner that you show that it cannot be 0?
Do you mean with writing like
let's say that you have G1 and G2, right? So that is of course has to be equal to some integer. So let's write it down, G1, G2.
a second.
It's difficult to write without a pen, isn't it? G1, G2 must be equal to some integer, just call it m or whatever, yeah, plus n times p, prime number. So this must be true, I think, because if I multiply two integers, I can always subtract an integer multiple of p, and the rest is, yeah. But what we do not know is what is this m? Yeah, so it could be that m equal to 0, right? So let's assume that m is equal to 0. So then we want to show that it cannot be.
Yes, and then we have G1.
G1, G2, go to NP then.
Yes.
Yes. So this would imply that G1, let's say, is equal to NP divided by G2.
Sorry?
So G1 then is equal to NP divided by G2. Yeah. So now we say that P is a prime number, right?
Yes.
And G2 is less than the prime number. So then P divided by G2 cannot be an integer.
Yes.
So unless P is equal to 1, unless the G2 is equal to 1, right?
Yeah.
But if G2 is equal to 1, then the G1 will be a multiple of the prime number, which is not possible because by definition, the G1 must be less than P.
Yes.
So that shows that it cannot be 0.
Yes. Okay.
Yeah.
And furthermore, we know that a multiplication between integers is associative, so that one is already certain. I don't think we need to. So that condition is also fulfilled, and our unit element E is just
That's 1.
1.
Yeah. But
then we also need to show that there is an inverse for
that's right.
each element, and I didn't come up with a good proof of that. It feels reasonable because if not, then we
yeah, it's a little bit tricky. Okay, so one way to show this is that so let's say that we have an element G1 and we multiply by let's say an element B.
Sorry?
Let's multiply G1 by an element B.
Yes.
And so we want to show that if we take another element, let's say C, so G1 times C, then we want to show that if B and C are different, then this cannot be the same.
Okay.
So if B not equal to C, then G1B cannot be equal to G1C. So we want to show that, I think. So the idea is that to exhaust the elements in the group. Because we have agreed that we multiply two elements, it will be in the group, but we want to show that it is not possible to have this equality, G1B and G1C. So then by going to the different B, we will exhaust the group elements.
Yes.
Yes, and then one of them must be 1. Yeah.
Yeah.
And that's the definition of inverse. Yes? So if G1B is equal to 1, then B is the inverse of G1.
Okay.
Okay, so we just want to show this. So how do we do this? So G1B must be equal to some integer plus NP, right?
Okay.
So
Do
we
you
write.
want to write it instead?
Okay, maybe I can share that.
I think you can write in this.
I can write here. Okay. Let me see. Can I do that? Oh yeah, I can do that. You're right. So let's say G1B here. So that must be equal to some integer plus NP. Yes, that's by definition. And then I have G1C. So let's assume that it is the same. Yeah. So we assume, this is often the usual trick, is to say that is equal to G1C. So then it's equal to M but I could have a different n, so let's call it n prime p, like that. So we agree up to now? Yes. So I'm assuming now that G1b is equal to G1c, and we want to show that this cannot be the case. So now if we subtract this, then we get G1 is times b minus c must be equal to n divided by n1, n minus n prime times p. But b is not equal to c. So then b minus c must be another element. So let's say d. But then we have G1d is equal to this, which is not possible. Yes, because that would mean that this is 0. Okay. So this implies that if b is not equal to c, then this two must be different. And then if I go through all the possible elements of b, then one of them must be equal to 1. Yes. So let's say we have 1, 2, 3, 4, 5, 6. Let's say we have a p equal to 7 like this. And I take an element G1 here, or let's just call it G. So this is G1, G2, G3, G4, G5, G6. We just showed that if I multiply by, if I multiply G by each of the elements in the group, then I must get different results. So this implies that one of these must be equal to 1. Yes, one of these elements. So we just exhaust the group elements. Is that does that make sense?
Yes.
Yeah.
I think so.
Good. Right, and the next one I think is simple, right? Just
Yes.
multiply.
Do you want me to do it for a specific?
Yeah, let's do it for the p equal to 7.
Okay.
Maybe even 5 is okay, but can try.
So we can do it for 5, I think.
Let's say 5. Yeah.
So then we
Then 5 should be in, yeah.
Right.
Yes. So we know that the group is abelian as well, which is good because then we only need to do half of the table.
Do the half. That's correct.
So
Yes.
and what we do is we just for everything that is below 5, we just write the number, and for example 2 times 3 is 6, and then we minus 5, so then it's 1.
Right.
And 2 times 4 is 8, minus 5, so it's 3. And then we have the same multiplication here as here, so then it's 1. And we saw that 4 times 2 is 3, so this is 3 as well. 9, 4, 12, so it's 2. And then it's 1 here, and
it must be 2. Yeah.
And
So it's
and it's the same procedure for larger tables as well.
It fits with the definition of a group. They're all different, row and column. They're all different elements. Yes.
Right.
Yes.
So for C, we want to show that a to the power of p minus 1 is
Yes.
equal to 1 for each element in the group.
Yes.
And I did it with the rearrangement theorem, or a similar version to it.
Okay.
So,
how do you do that?
So we know that if we have an element, or if we have an element x, and do the and relabel everything, g goes to x g instead, we get back to group again. So for example, if because we just rearrange our multiplication table, where x is in G, and yeah, so we have this map, and then we can take the multiplication of all overall elements in group G. So G is in our group, but this is the same thing as multiplying over these elements x, g, because we said that this is just a rearrangement of this, or all these. We just rearrange the factors, but we all have all the same factors in this multiplication.
Okay. So what do you mean by the right hand side is that you multiply each element by g?
No, it's that we multiply each element in the group together. So for example, 1 times 2 times 3 times 4.
Okay, and on the right hand side, what do you have?
We multiply this row, for example, with the number, so we get one of these rows instead, but we all have all the same, we have the same elements, we just have a different order.
Okay, so so what you mean is that maybe I can write here. So what you mean on the right hand side is that you have by g of ag like this.
Yes.
A is any element in the,
yes.
the group.
So x here is any element in the group.
Yeah.
As we said here.
Yeah.
But the group is abelian, so we can take out all the x's, and we have p minus 1 of them.
Yeah.
And then we have still g in E over group elements, and then we can just cancel these, and we see that x to the power of p minus 1 is equal to unit element for all x in the group, which is what we wanted to prove.
That's correct.
And then D is just checking, and it's pretty straightforward too. I don't know if you want me to do it because it's just verifying that this works.
Yeah.
For example,
yes, that's easy. The last one.
7 minus 1 is equal to volts, and etc.
Yes. Okay, so that's one way of proving the theorem. Actually, I did it in a bit different way. maybe I can share. So.
Yes, I can clear this.
My reasoning is something like this. So let's say I take an element G, then I say that there should be some integer n. So this is the order of the element is equal to E. Yes. So G, G2 and Gn then is equal to E, which is form a cyclic group, because we can always take an element and then form a cyclic group, yes, from that element. We can always do that. So then I have a subgroup of order n. So that we know that p minus 1, which is the number of elements in the group, divided by n, which is the number of elements in the subgroup here. This is a subgroup. Must be an integer, yes. Must be integer. Let's say m, like this. So then g to the p minus 1 must be equal to g n times m. So that would be equal to gn to the m. But gn is equal to e, so then this is equal to e. So that's another way of proving the theorem. But what you did is also fine. And then we have then the Fermat theorem, that since this is equal to E, that would imply that G to the P is equal to G, which corresponds to N to the P is equal to N modulus P. Yes. So, is there any question about this problem? It's quite interesting, actually.
Yeah, just give me a second to think about this. Don't remove it straight away.
Okay.
Yeah, could you reiterate the second line? Just why must p minus 1 divided by n be an integer?
Because of this theorem, yes, that if I have a subgroup, so this is a subgroup. We know that the number of elements in the subgroup must be an integer divisor.
Okay.
Yeah.
Oh,
So I don't know, I think it's called the Lagrange theorem or something. Yes.
No, that's really neat. Okay. So I had a question also about the previous solution that we looked at.
Yeah.
Adam's solution. So what you showed was basically that the multiplication of all these numbers right. Adam, you showed this and then you divide it by.
Yes.
We've shown that, I mean, maybe I'm being picky here, but we've shown that this is sort of the identity element for this particular one. That's, we have some number times x to the power k minus 1, and we get the same number back. But in order for something to be an identity element, it must be identity for all other elements, right? Would it be possible to create a not a group, but something else? where you have an identity that, well, okay, maybe because we know it's a group already.
Yeah, I mean, this X is an element in the group, right? Any element in the group.
Yeah.
And that equation is true for any X.
Right, and there's only one identity element, so
There's only one identity element, yeah.
yeah. So assuming you find one instance where an element is the identity, then it is the identity. Yeah. Okay.
Yeah.
Okay.
Yeah.
Okay.
Very good. Are there any questions about this? So the first exercise is mainly a bit mathematics, basically. Yeah. And I will upload the second exercise hopefully today. I should have time to do that today. Yeah. So are there any questions about exercises or the courses so far that you would like to raise? In this, we have a little bit time, remaining time, a few minutes. Yes, I hope you could follow the course reasonably well. It's a bit difficult with this Zoom lectures. It's much nicer to give a live lecture in the lecture hall. And I think the difficult part is that I cannot see how you react when I say something. Okay, so if there are no further questions, then we just stop here perhaps, and we meet again Wednesday, Tuesday for the next class. Yeah, very good.
Could I suggest, by the way, just
yeah.
for next week's problem session, maybe there would be
Yeah.
a way with breakout rooms or something like this, where, because right now we have 20 people on the call sitting quietly and listening to one person present.
Okay.
So maybe, I don't know.
Yeah.
Maybe people would prefer to have breakout rooms or smaller groups where you can discuss, because when there's 30
I
people
see.
trying to, I don't know if that's a good idea, but that's just my insight.
Mm-hmm. Okay. I'm not a pro on using the Zoom, but I can ask someone to do this. How to do this? That should be quite straightforward to do.
Do people think it's a good idea to have breakout rooms?
I don't know. I kind of like this, but I don't know how the breakout rooms will work, because then it's many people and.
Yeah.
I mean, I'm happy to stay like this too. I don't mind it.
Mm-hmm. So your suggestion is to have, let's say, 6 groups or something. Let's say that we divide it like in the, well, it should be in the same group like as it is listed in the website, or what do you think?
I don't know. I think because it depends on how many people show up each time.
That's true.
Because maybe some people show up and some people don't. So maybe it's just better to each time just assign some people into breakout rooms if they want to. Leave it flexible in that sense.
And then you can discuss things within the same group.
I think that would be, at least for me, that would help me more maybe than sitting listening to one presentation at a time.
I see.
I don't know if people agree. Lassie didn't agree, but
yeah.
But I think.
I mean, from my
I'm just thinking, because then we can't really have 30 in every room, or this is like one group is stuck with something.
Yeah, but then 30 can go around and help us, right? That's what I was thinking.
Yeah, maybe. Yeah.
Mm-hmm. Okay, let me think about that. So any other suggestions?
It's questions which are obviously easier, then I guess a breakout room could result in a more fruitful discussion. But perhaps if we have a more difficult problem, then maybe it would be, as Lassie said, we might just get stuck on something. So maybe it's nice to have a breakout room if it's easier questions, so people could just discuss, and then maybe you learn something which is not in the question directly, but so it could be a good discussion, as Felix said. But maybe it's a difficult question. It might not be that good of an idea to have a breakout room. That would be my personal outlook.
So you prefer open rather than?
But I guess if it's some normal questions and you could have a general discussion, that could actually be good. But maybe you could have, if it's more difficult questions, obviously, then I would prefer to be in the open discussion like we have right now. But maybe if it's easier questions, then I wouldn't mind being breakout room.
I see. That's true, of course. I guess the way we are doing it now, we can all share same thing. Yes. Yeah. Yeah, I don't know what would be the best way to do this.
I guess we can wait, because I think if you at least enable breakout rooms, there's some setting somewhere you can enable that, and then we'll see who shows up next week. Maybe the people who show up next week don't want to do it, or maybe they do. We'll see. Deciding now, there's no point.
Okay. Yeah, we can try, but we'll see.
All right. Thanks for today.
Okay. Very good. So we'll say goodbye then. Good weekend.